our project is called ShallowSleep, and the main idea is that we're using machine learning to track sleep stages. And we'll get into why that's kind of an interesting problem in the next slide. So obviously, like, sleep is a really important part of our lives. We do it every night, but it's something we don't really pay that much attention to. And if we want to, like, get more sleep or see, or even like cure possible, or like not cure, but see if we have diseases that are kind of indicated by sleep, like, I don't know, depression, it's not really a disease, but other things like Alzheimer's and stuff, like early onset, can be detected by sleep. If we want to see any of those things or detect those things, we need to kind of like get a real good analysis of our sleep, which is something that's kind of hard to do in today's society. So yeah, tracking it is good, is the main point. So if you do, let's say you do actually want to like track your sleep for a certain night of sleep or few nights of sleep and get really accurate results. The only really, state-of-the-art way to do that right now is by going to a sleep lab. And although you do get, the most accurate results you possibly can, but still, like, unfortunately aren't that accurate, it's super expensive. You have to wear these uncomfortable, like, sensors all over your body, like electrodes plugged into your head, and like, a bunch of other sensors just attached to your entire body. And you need to sleep in like a bed in some sleep lab. You can't actually sleep at your own house. So you could think that you're not really getting an accurate reading of your own sleep in that way, since it's not even like a true night of sleep in your own bed. Plus, in order to actually like label this data and see like what sleep stage you're in at a given time, you need to hire these sleep experts to like just look at your entire night of sleep and all the data and just label it by hand. So not the best. Because of this, people have tried other methods for tracking your sleep, such as using like Apple Watch data or Fitbit data, or like some other types of heart rate monitors that just strap around your waist. And although it's, more convenient, you can sleep in your own bed, and it's a lot cheaper than going to a sleep lab, it's super inaccurate because motion is just a really bad indicator of sleep. And, although heart rate is something that can help finding out what sleep stage you're in, it's not really enough. And that's all these sensors really give, like motion and heart rate. So that stuff doesn't really work either. So the big question is there some way to like track your sleep at home that's, accurate and non-intrusive and cheap, all like at the same time? So one other method that we didn't mention is using radio frequency data, which is just having a little radio transmitter, like super low power, like I think 1,000th as powerful as your cell phone, just sitting next to your bed, that just kind of shoots off radio waves and analyzes their reflections. And the idea is that way it can kind of like get a sense of what you're doing as a whole. It can resonate with your heart rate and breathing, so it can kind of measure those things as well. So it theoretically gets all the correct data, but the only problem when you try to like feed it through an ML model, as this little animation shows, is that radio frequency data is like super, super, super noisy. Specifically, let's say you train it on like some guy sleeping in his bed in like, I don't know, unit 1 or something. And then you try to test it on some dude sleeping in Martinez or something like that. Like a room in Martinez is going to be completely different than a room in unit 1. The bed size might be different. The person might have a different body size. The device might be farther or closer away. Plus there might be different types of electronic devices in that room that are shooting off their own radio waves that interfere with the signal. The main idea is like the difference between what you train this data on and what you test it on is going to be so different that most of the papers that have actually tried using radio frequency data were like really unsuccessful. They didn't really do much better than normal watch data, just because this data is so noisy and it's really hard for an ML model to kind of take away all that noise and extract the sleep stage. But Pardue, who's also in this club, showed us this cool paper that came out of MIT, where they used a really unique adversarial architecture to deal with this problem. So if we go to the next slide, the overall model, instead of just being one neural network that takes in radio frequency data and outputs the probability that you're in a certain sleep stage, is we use this kind of 3 model game architecture, similar to a GAN, where we have an encoder that takes in the radio frequency data and just encodes it into some latent distribution, and then a predictor that takes that latent distribution and outputs predictions for what sleep stage you're in at a given time. Like that's pretty obvious. But then we also have a discriminator that tries to guess what sort of situation that data came from. We're going to call this the source going forward, but pretty much what the source means is just the room size and the body type of the person and all that stuff. And the way it's encoded is just for each, like obviously this data came in, the data that came in was just like a bunch of nights of sleep from different people in different, rooms and whatnot. So the source is just each one of those people/room pairs is assigned a number, and the discriminator tries to predict like the correct number label for a given source given the encoder's latent distribution. And we'll get into like the details here a little bit more like later on. But the main idea is that the predictor is trying to kind of work with the encoder to pull out all the information from that radio frequency data relative to the sleep stage that the person is in. And the discriminator is trying to get the encoder to clean out and delete all the information relevant to like, the room size, the body type of the person, what other electronic devices are in the room, anything that lets it kind of tell what sort of situation the data came from. And theoretically, if we train this enough, then we're going to have this like encoder predictor model that takes out everything relative to like or relevant to the source so that we can then kind of test this or use it in situations that it's never been trained on before. That's the main idea. Next slide.
Okay, so now we're going to talk about how we train the model before we go into the details of like the encoder, the predictor, and the discriminator. So to give an overview of like our data, as Max was saying, like we get however many nights of sleep radio frequency data from every like room person pair. We then like take a batch of this. So those like rectangles, each like night of sleep is separated into 30-second intervals, and these 30-second intervals have a classification for like awake, as you see, is yellow, and the like green is N1 is green in this case. So each of those rectangles represent like one spectrogram that we generate from the radio frequency data, and then we have like 5 channels of those. We then take the sequence of like maybe like 5 minutes worth of data, and we pass it through the encoder to generate an encoding output. That's the next, yes. Yeah, so it goes through the encoder, we get an encoding output. This then goes into the predictor, and the predictor just uses the encoding to predict a sleep label for the data. And if we're passing sequential data, then the predictor would be outputting like a sequence of labels corresponding to each 30-second interval. But yeah, in this case, you see it's like N1. Then afterwards, both the encoder and the predictor, their outputs go into the discriminator, which then tries to predict like which room person pair this comes from. And then finally, we train the encoder and predictor according to the loss function defined in the top line of the slide. Basically, LF is the loss of the predictor, and LD is the loss of the discriminator. So the predictor is trying to minimize its own loss and then like maximize the discriminator's loss. So trying to make it so that the discriminator can't tell which source it came from. And then after we train the predictor and encoder, then we train the discriminator, which goes for like, it's operating off the same loss function, but this time it's trying to maximize this loss. So decreasing the loss of the predictor and then increasing its own accuracy. And then we train this up to a certain threshold, which I think people will talk about later. But yeah, this is just done on repeat until we get a good accuracy.
Yeah, so now we're gonna go into like a bit of the specifics of each model that we used. So as for the predictor, what's gonna happen is like we're gonna go over the encoder later, but what we expect it to do is gonna take our data and it's gonna like do a bunch of stuff, and it's gonna turn it into a 1D like vector of like some length, and then that 1D vector is like all we need to predict the sleep stage, because it tries to like remove the source and give us what information we actually need. And so we're going to feed it through this predictor, and it's going to give us the sleep stage, or like the distribution of what it thinks the sleep stage is. And so to do this, we like just need a simple linear layer of like two layers, and then like we take the encoder output, we pass it through our linear layers, and we get our output of like our 7 different like stages. And then our loss function will be like the cross entropy between our predicted like sleep stages and the actual sleep stage. Yeah. And then as for the discriminator, what's going to happen here, like one thing that's like kind of interesting to note is the fact that there are like 2 inputs. And one input is like the input from like what we predicted the sleep stages to be. And the other is like the encoded input that we like fed into the predictor. And the reasoning behind this, like why we have to like feed the results of the predictor into here, is because if we didn't have that, like one way for our model to like quote learn is by just removing the source from it. And like this screws up the predictor because like it can't really predict the actual sleep stage, but it also screws up the discriminator. And this is like, this actually kind of works for like the encoder like loss function, because although the predictor may be bad, the discriminator is also bad. So the loss is going to be pretty low, which is good for it. So to fix this, we actually like feed in, we want to feed in like the probabilities of some sleep stage given like the data that we have. The thing is that we don't actually have like the probability of some sleep stage given like the data that we're feeding into the encoder. So the best way to approximate this is by getting the probability of sleep stage from the predictor given some like encoded output. And this is like kind of the same thing if you can imagine in our like optimal situation where the encoder gives like the best output and the predictor like takes that and predicts the sleep stage. And so we want to feed that in, and with that information, the discriminator can actually now like use that information, and the encoder can just like do like this easy trick of just removing the source. And yeah. And for our discriminator model, what we're going to do is we're going to take the encoder outputs and the predictor outputs, so like the output and the probabilities of each sleep stage, and then we're going to feed it through our linear layers, and then the result is going to be like some prediction of what the source would be, like what person in the room it came from. And oh, what the hell? Yeah, and then our loss will be like the cross entropy between like our source and our predicted sources.
Yeah, so now we're going to talk about what our choice for our encoder is. And the main things we want to do with the encoder is, one, within a 30-second spectrogram, we want to show the relationships within that 30-second interval. So we want some spatial similarities to be captured. And also note that a sleep stage is obviously going to be longer than 30 seconds. Like if you fall into REM sleep, you won't, I mean, most people wouldn't just wake up after 30 seconds and move on to another sleep stage. So we want to find some similarities between these 30-second intervals. So we want something to catch temporal similarities. So first, to work on the spatial similarities within 30 seconds, we tried a standard CNN. And this worked fine, but again, this doesn't capture anything between the 30-second pieces of data. So then we added on an LSTM to capture the temporal similarities. And this kind of does what we originally wanted it to do, but the validation accuracy is quite low just because it doesn't, the CNN isn't able to go through many layers before losing what the original information it had. So we switched over to a ResNet instead of a standard CNN, and a ResNet is much better in this case because, so basically what happens in a ResNet is, let's say you have 5 layers, and at the end, well, obviously, let's say you have like 30 layers. If you just go straight through all the 30 layers, at the very end, you will basically have lost a lot of the original information that had arrived in the beginning. And that makes it hard to predict, especially if you want to keep, you need all that information to predict your stage. So instead, a ResNet has what's called a skip connection, where you can just concatenate or add on the original data to a deeper layer. So even as you're learning through the layers, you're not losing the original information you got. And again, next slide. we still need the temporal information. So the encoder formation that ended up working the best was the ResNet for these skip connections to analyze 1 30-second spectrogram, and the LSTM to analyze between the spectrograms. Yeah, so overall, as everyone else mentioned, we get labeled data that is basically originally like a waveform with amplitude and frequency. We turned it into a spectrogram to work better with our model, and it goes through an encoder, and then the predictor and discriminator and encoder work to like kind of play against each other adversarially to try to make the encoder and predictor try to make the discriminator fail, and the discriminator tries to make the encoder and predictor fail. And ideally at the end, we have an encoder that only encodes the information necessary to predict the sleep stage and discards everything that is like relevant to what room a person is in, what body type, and all that other noise.
All right, this is me again. So before we kind of get into the results of the model, I'll quickly kind of talk about how we exactly train like the discriminator and the encoder and predictor in tandem. So for those of you who are familiar with GANs, normally like a really difficult thing, or at least something that you need to tune a lot, is like the relative learning rates between the discriminator and the generator. If you have a generator that's generating images and a discriminator that's trying to pick out if the image comes from the generator's generation or if it's like a real image, you don't want the discriminator to get like too far ahead of the generator, because then the generator just won't really be able to like learn off of the discriminator and improve. Likewise, you don't really want the generator to get too good, or it wouldn't really be too good, but you don't want its loss to, decrease that much. I guess this isn't a great scenario because its loss is just determined by the discriminator's loss. And in this case, we have different losses we're worrying about. But the main idea is you don't want the generator to like get too far ahead of the discriminator. You don't want the discriminator to get too far ahead of the generator, because then they don't really learn well off of each other and improve each other. And we have the same case here, where obviously we wouldn't want the discriminator to just filter out all this data about the source from the encoding before the predictor can even really pull out relevant information about the sleep stage. And likewise, you don't want the encoder to just you don't want the predictor to force the encoder to just keep everything in that encoding, including the source and all that, and completely like screw over the discriminator, because then we won't really be able to generalize to new situations with different types of sources that we haven't seen before. So the solution to this is we have like this really cool tool, and the MIT paper, this is probably the most unique thing about the MIT paper, in my opinion, where since we have labels for the discriminator, and we're not just trying to like predict generated stuff from a generator, we can use those to our advantage. The way we do that specifically in this case is we train the discriminator until its loss equals the entropy of the source distribution. That's kind of like the technical way of saying it, which probably doesn't really mean much. So if we break that down a little bit, the entropy of a distribution is the loss that a random guesser would get on that distribution. Entropy means a lot of things, but that's kind of the more relevant definition here, specifically the cross entropy loss, which is the loss we're using in this case. And the reason that's so helpful is that we can use that to kind of balance out the discriminator and the predictor. So the way we do that, as this training loop shows, is we'll first train the encoder and the predictor on one batch. We'll just sample a batch and train the encoder and the predictor once on it. And then we'll go over to the discriminator and kind of ask, okay, what's its loss right now? And if its loss is greater than the entropy of the source distribution, that means it's doing worse than randomly guessing. So obviously the discriminator is behind the encoder and the predictor, which we don't want. So we'll just train it and keep training it until its loss falls below that entropy, which means it's doing just a little bit better than a random guesser. And then we'll switch back to the encoder and the predictor and train them for an epoch. And then we'll check in with the discriminator again. And we kind of keep doing this switching off training loop in order to keep the discriminator constantly at like a perfectly fooled state. And that's what we want. If the discriminator is like doing way worse than something that's just randomly guessing, then it's not really going to be taking out the information we want it to from the distribution. And similarly, if it's doing way better than random guessing, that's kind of an indicator that the predictor isn't doing really well either. And the encoding is just too far skewed towards what the discriminator wants. So if we keep it perfectly balanced, then we theoretically keep the encoding perfectly balanced between retaining information about sleep stages and discarding information about, the type of person that actually has those sleep stages and the type of room they come from. And theoretically, if we train this for enough epochs with this sort of structure, keeping it in balance, then we'll reach like a perfect encoding that retains the information we want and discards the information we want so that we can generalize this to new types of sources. So with that out of the way, we can move on to the loss graphs. So if we look at the first 50 epochs, we can see that like not much is really happening. And also, I'm saying epochs, but really these are just batches because that's kind of how our training loop is structured. The source discriminator loss decreases a little bit. Everything else is pretty constant. But if we then look at the next 500 or so epochs, now stuff actually starts happening where our training accuracy is going up. It takes a little bit for validation accuracy to catch up, but eventually we do get there. And then we're also tracking this other metric called Cohen's kappa, which, just to give a quick explanation, is a metric that's specifically designed for measuring the accuracy of sleep stage classifications. The reason it exists is because, as I mentioned like way back at the start of the presentation, the state-of-the-art way of going to a sleep lab and getting sleep experts to look at your data and just classify what sleep stage you're in at every given 30-second interval is like not great. There's a lot of human error that can exist, and specifically if two sleep experts classify the same night of sleep, they're only going to agree with each other about 80 to 85% of the time, which is far from perfect. So Cohen's kappa is just kind of a metric that exists to factor that in, but it's a little less intuitive than accuracy. So if we just focus on accuracy, we see that we end up getting like a little above 70%, which in a normal ML model would kind of suck, or at least not be great. But factoring in the fact that like the best we could possibly hope for is 80 to 85 for specifically classifying sleep stages, this actually is pretty decent overall. And, you get this from just radio frequency data, not all these fancy sensors like hooked up directly to a person's body in a sleep lab. So when you think about it, it is pretty cool. But yeah, now that we've kind of gone over the results in the model, we have another kind of exciting thing to show you guys, which is a little web app visualization, kind of like a demo of what it would look like if you could actually, like, I guess, record a night of sleep with a radio device and then upload it to a website to see like a little summary of your sleep in much more detail than Apple Watch or anything else gives you. And I'll let Rachel and Patrick and Nisha present this because they were the ones who did it.
All right, hope you guys can see it, but yeah, so this is like kind of a visualization of what our like model's outputs like generated, and like because like our model outputs like would generate the probabilities, and we like put these probabilities like visualized in our like website. And so what this looks like is like here's a line graph of like the probabilities of like what we predicted each of the sleep stages to be over time. So as you can see, like we maybe like predicted like this is like definitely going to be like an N2 sleep stage somewhere here, and then like over time like maybe we see a bunch of like REM cycles coming up, and like as you can see like kind of like sort of low peaks, but yeah. And so like one thing to know about our data is that the data that we use is that there's like an error label factored into it, and like this is because sometimes with their measurements, like mistakes can happen and they would have like an error. On our part, there's like virtually like no reason to have an error. And so in the case of our data, like we always predict the error to be 0. And yeah. And if we look in the proportions of like the sleep stages of what this look like, we would see that N2 corresponds to like around like 46% of our sleep cycle, what we predicted it to be. And that kind of makes sense because for the average human, like they usually spend about like 45 to 55% of their sleep inside N2. So it's like perfectly reasonable. And as for like the REM, like we predicted it to be like somewhat like low, like around 10%, but like the average is around 25% of our sleep cycle. And that's like mainly because like we noticed like these REM cycles, as you can see, there are like peaks there, but like we don't get them to be like determined as like this person is acting in REM. We usually say they're like in N2 or something, and that's because most of the time people are in N2, so like the model's kind of more inclined to say you're in N2. And yeah, so like also one thing to note is like the least common stage is N1. You know, like kind of makes sense because you usually spend like 10 minutes in N1, and so that's like very little time. And yeah, that's about it.